A common nonlinearity that shows up when modeling physical systems is the saturation function. One reason that this often shows up is that most actuators have physical limits. Take for instance a valve. You can open the valve by turning it up to a certain degree, and then it is physically impossible to open it any further. You may be able to continue turning the valve input, but the flow through the valve will not increase. This can be represented by the saturation function, which in normalized form is given like this. As long as the input is less than a certain threshold, the output is equal to the input, which in this example means that the actual control input is equal to the desired control input given by the PID feedback control law. When the desired control input exceeds the actuator limit, however, the actuator is not able to give anymore, and the actual control input is constant and equal to this maximum, regardless of how high the desired control input is. Even if the process can be described by a linear differential equation, like in this example, and we have designed a linear PID control law, such an input saturation makes the closed-loop system nonlinear. The saturation function is a memoryless nonlinearity, meaning that the output of the nonlinearity at any instant of time is determined uniquely by its input at that instant. It does not depend on the history of the input, what has happened earlier, so the nonlinearity has no memory, no dynamics. The saturation function is also an example of a hard nonlinearity, meaning that it cannot be linearized. It cannot be approximated by a linear system. This is because the derivative of the function is not defined here and here. Such nonlinearities can typically generate a particular type of oscillations, something that we call limit cycles, and which we will get back to later. For other systems, you may find when you model them that they can be linearized, but that the linear approximation will be a poor representation of the system because there are nonlinearities that are essential in the model and which disappear when linearizing. Take for instance electric motors in hybrid cars. Without going into the details of the model, you can notice that there are quadratic terms here, like here we have the state omega multiplied with the state lambda r. And if we linearize this model, these quadratic terms will disappear, and it can be shown that the resulting model will not give an adequate description of the motor behavior. Other well-known examples of models that have essential nonlinearities are models of weather prediction, which typically display very complex dynamics. In 1963, Edward Lorenz developed a mathematical model for atmospheric convection. This model consists of three ordinary differential equations, which are often called the Lorenz equations, and which we see here. And even if they look rather simple, the system behavior is quite complex, and a linear approximation of this model is not able to describe this kind of behavior. In particular, the system displays what is called the Lorenz attractor, a set of chaotic solutions which resemble a butterfly or the figure 8. So these are some examples of systems where the nonlinearities are so essential that it is not adequate and sometimes not at all possible to describe the system behavior by a linearized model, because nonlinear systems may display complex behavior that linear systems just cannot reproduce. Sometimes it can be the variation in operating conditions that make linearized approximation inadequate. Remember that when we linearize a system model, we replace it by a linear approximation where the system matrix is the Jacobian of the nonlinearity evaluated in the operating point. And when the system is operating far away from this point, the linear approximation is no longer a good one. Furthermore, when systems operate in extreme conditions, the nonlinear effects may become particularly significant. In this video here, we see a motorcyclist pushing the limits, something which generates unwanted oscillations. Another example of a system which has complex dynamics which cannot be adequately described by a linear approximation is the HIV virus dynamics. The dynamics is nonlinear. We can see the quadratic terms here and here. And it is highly non-local, meaning that it will typically not stay close to one operating point, but instead the states will vary over a large region. And the linear approximation around a single operating point will therefore not be an adequate representation of the real system behavior.